It should be immediately obvious that understanding power series should grant us serious power. So let's try to remember the geometric series. Geometric series was something like 2 to the n, where we had this fixed r that was just a strict number, the 2 that was just our r constant, right? And then in our power series, though, we're going to have x to the n. So the r has become a variable. We don't know what x is. But remember that, if we wanted things to converge, that the absolute value of x should be less than 1. So that's going to be really important in the power series. Now let's write this out in long form. So it's going to be n equals 0 going to infinity. We have our constant. Now, and every time, back in the day it was a, right? But now a is not going to be constant. It's going to be changing. This constant is going to change for every n. You're going to have a different constant. So instead of a, it's going to be a c here. And then we're going to go over here to x to the n. And this is going to be for every position. C0 might be a different constant there. You might have a different constant here at x. And then you might have a different constant here at x to the n. All right. And this is kind of how the series will continue over here. Once again, if we have the absolute value of x being less than 1, it's going to converge. And if we have the absolute value of x being greater than 1 or equal to 1, it's going to diverge. And so those are some things that we just have to, the only time this is really going to work is when x is less than 1. And then we can rewrite this if we have, for example, a center. Okay, keeping in mind, this one here is at the origin. This will start right here at the origin, this power series. So it's centered at the origin. Over here, we would have something that's centered at maybe this center of A. So x minus A. So now the center of this power series is going to be at x, or whatever A is, on your x-axis. That's where your origin is going to be. So this is the center at A. Okay, and you're going to have the x minus A. In this position, A is 0, and so that's why that's the origin. And over here, we're going to go C0 plus C1, x minus A, and then plus C to the n, sub n really, x minus A to the power of n. This will continue. And that's going to be something centered at A. And this is just how you would write power series out in long form, and understanding that it's going to be a variable x instead of the fixed r there. And this will only work if x is less than 1. Now this whole x being less than 1 concept is pretty important because we've got to figure out what is the interval of convergence. We plug it in here and we could see, okay, yes, x can actually go from here to there and it'll still make this whole thing work properly. We have to go through this process. First, we either got to do the ratio or the root test, on whatever function we're trying to, whatever series we're trying to look at. Then we want to achieve r being less than 1. So when we do the root test, we're going to get this r, right? And we want to make sure that's less than 1, so that way it will converge properly. And in order to do that, we have to solve the inequality that we're going to get. Remember that the ratio or root test will give us an inequality. We've got to solve for that with our function. And number 4, then we have to test the endpoints. Test the endpoints on a timeline to see whether it will actually converge at the end or diverge at the end on those specific points. So then you could find the whole interval. Here are some examples. Let's just say we managed at the end of a ratio test to get something like x, the absolute value of x, and n goes to infinity, 1 over n plus 1. You notice that as n goes to infinity here, this side becomes 0. And so no matter what you put in for x, it will always be 0. And so r will always be less than 1. And in this situation, all real x's will converge. Okay? Now, let's take a look at this example. We'll say maybe at the end of the ratio test, you ended up with, as x, as n goes to infinity, n plus 1 over here on this side. Well, in this case, this is always infinity. And so no matter what you put in there, it's only going to work if that is a 0, right? If that's 0, if x is 0, then r will be 1, okay? Because this is infinity. So that will make it work. So if x is 0, x equals 0, we've achieved r is less than 1. This is the second step, right? And you might also go into the next stage being something like this. X minus 2 is looking like that. with the absolute value around it. Now you don't have any kind of limits here, so you're thinking to yourself, okay, what can I do to make this be less than or equal to 1? All you need to do is go -1 is less than x minus 2, which is less than 1. And now, when you solve for that inequality, you'll find that all of a sudden, this will make that work for r is less than 1. So you might have to solve some inequalities here to make that work. Once you solve for the inequalities, especially this one right here, then you'd want to test the endpoints. So that way you know, okay, you've got your center at A, whatever A is, in this point. In this particular situation, A is 0, but you may not have A being 0. And then over here on the right side, you'd have A plus R. So let's say on this situation, we added 2 on both sides. We would get 1 and then 3. So 3 would be over here, and then 1 would be over here on this side, A minus R. So you get this whole R being this like radius of convergence over here. And, you know, in this particular situation, it's 1 to 3, but in other cases, it might be -1 to 1 or whatever. So we're trying to find the radius of convergence here. And then what you want to do is make sure that you mark that in your inequality by saying, you know, okay, so it might not, it might diverge there. So you might put an X, it would be open, so it would be the less than sign or something like that. And then over here on this side, it might actually converge. So you'd fill that in and you'd call this, you'd say, hey, that works out. And then you put an equal sign on that side to represent that, for example, you just go like that, right? To make sure that that works and that one doesn't. And that's how you can test for the interval of convergence for these series. Remember that the solution to the geometric series was going to be A divided by 1 minus R when R was less than 1. Well, we have this case for the power series. A 1 over 1 minus x is the simplest power series. We can rewrite this like this. We get the x to the power of n. That's going to be equal to 1 plus x squared. And this continues. This is our most basic power series, and then from here we could start doing some other interesting things. If we instead replace the bottom x with an x squared, 1 minus x squared, then we would just plug that back into the formula up there, and we'd say x squared to the power of n, and that's going to equal 1 plus x squared plus x to the 4th, and this continues. Now we can also go on this side and say, okay, 1 over 1 plus x. We would have to remember that this is the same thing as saying 1 minus negative x. And so let's use the same formula, but let's plug in negative x into that. And now we'll get 1 minus x plus x squared, and this will continue in some pattern. Now, we can go down here and go 1 plus x squared, okay? We'll just do this. Again, these are some simple ones that we just kind of need to know. This is negative x squared up here, of course. And this will be 1 minus x squared plus x to the 4th. We can also take derivatives and integrals of some of these series. So let's go, for example, 1 over 1 plus x squared. Let's remember that that is actually the derivative of negative 1 over 1 plus x. And so if we were to turn this into negative, this is negative, the negative 1 plus x minus x squared, and then take the derivative of that, well, this will just go away. And then so over here, this would be a plus x, and that will just turn into a 1. And then over here, this would be like a minus x squared, which would turn into minus 2x when you take the derivative. And then this will continue and form plus 3x squared and stuff like that, and so on. So you'd have to sort of look at that. We could also say 1 over 1 minus x squared is just the derivative of 1 over 1 minus x. And so when we solve for that over here, that would just be 0 here, and then plus 1, and then plus 2x, and then plus 3x squared, and that stuff will continue. We can also take the integral on this side, so ln of 1 plus x, that's just the integral of 1 over 1 plus x. And so if we take the integral of this one, then we'll see, well, this will turn into x, and then this will turn into minus x squared over 2, and then plus x to the 3rd over 3. And that's going to be for ln of 1 plus x. This is pretty easy stuff. And then we can go into the next one, which would be like, say, arctan arctan of x is going to be the integral of 1 over 1 plus x squared, right? And that would be this one that we already did. So let's just take the integral. We get x minus x to the third over 3 plus x to the fifth over 5. And now we can start seeing how this is actually pretty easy stuff. So when you have one of these power series centered at a fixed letter A, over here was just the A, that's the power series. But over here, if you actually have a number, then it would be a Taylor series. And if that number is 0, then it would be a Maclaurin series. And if the series will continue until infinity and goes to infinity. But if you have just a partial polynomial, Maclaurin polynomial, or Taylor polynomial, that would just be n equals 3 or something like that, some sort of small number of n. So that way you could start to estimate certain functions with the polynomial. Now sometimes we need to figure out what the coefficients are of these series. So let's try to do that. We're going to need to use derivatives. So we're going to use the nth derivative, and then we have to plug in the a that we have, the center, at that point. And then we're going to start continuing the formula like this. The n factorial on the bottom, and then we have that part. So you can see that this is essentially what the coefficient would be. That's what Cn is. Cn is equal to this thing. And so now we can start writing this out. So Cn in this particular situation was f of a, and then over here we've got f prime of a, x minus a, and then this could continue double prime a over 2 factorial times x minus a squared, and this would continue on until you stop. Great. So this is great if we're trying to estimate certain things. And let me try to write this out for example, f of x equals e to the x. And we want to try to find some coefficients of that. Well, remember that first we're going to have to start taking derivatives. So the derivative of f of x is e to the x, and the derivative, the double derivative, is also e to the x. Now this is an easy one because it's always e to the x. So as you keep taking derivatives, it's always e to the x. That's great. And then if we plug in, let's say we had an origin at 0, that was a Maclaurin series, then we would know that if we plug in 0 for there, we just get 1. And so that's going to be the first coefficient there, or part of that. So I'm going to take the derivative here, just going to plug in all these things into 0. Just make a little chart, and you just find every single time it's always 1. Now this is an easy one. Usually it's a little bit more complicated, but I just chose the easy one to make it simple. And then over here, if you would rewrite this, you could say e to the x is equal to the series here, infinity, x to the n divided by n factorial. That's because when we go 1 plus x squared over 2 factorial, we could start to notice that this was 1, and then there's a 1 there, and it's x minus 0, so it's just x. And over here, this was supposed to be the double prime, which is supposed to be 1, and then over at 2, right, 2 factorial, so that part is good. And then we get the x squared that comes from this, because x minus 0, x squared. And so that is how we built up this thing, and it's just kind of like, whoa, okay, we just built that up real quick like that. Let's also notice the next things, like for example, sine of x, just a couple more. It's going to be n to go to 0. We're not going to write out all the f of x's and stuff. We're just going to simplify that to -1 to the power of n. And then we've got x to the 2n plus 1 divided by 2n plus 1 factorial. And that's just going to be equal to x minus x to the third over 3 factorial plus x to the fifth over 5 factorial. And this will continue. These are all the odds. And for the cosine x, then it's going to be n equals 0, -1 to the n, and then it's x to the 2n divided by 2n factorial. And this is just going to be equal to 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. These are some easy ones that we should already know. And in this case, this is just Maclaurin series because a equals 0, so I plugged that in there. All right, and so that's pretty cool. Now let's understand that when we make one of these Maclaurin polynomials, there's going to be some kind of a remainder. at the end, because we're going to have this remainder, because we have the original f of x, and then we're going to be subtracting the polynomial that we found. Because remember, the original f of x goes on forever, but the small polynomial stops at a particular n. So once we delete that part from the whole thing, we're left with the remainder, right? That makes sense. So this is the Rn is fx minus Pn. That's whatever we have over there. So if we started to try to solve for this, it would be, you have to start using some more of these derivatives, which is very similar to what you do over there, but be something like this, n plus 1 factorial. And then this is of c now. Instead of f of a, it's going to be f of c here. We don't know what c is. So we did know what a was over here, but we don't know what c is. So we're going to have to figure out what c is. And then we also have put this with the x minus a and another n plus 1 over there. This is how we could solve for the remainder. Furthermore, let's keep going. Once we try to actually solve for this with some numbers, we realize the absolute value of that is equal to, we got to plug the max value here, the max value, and then it's n plus 1 to the power, and factorial there, and we got x minus a to n plus 1. Let's say we wanted to estimate the cubic root of 11. We could start with, say, for example, the cubic root of x, and we can also choose whatever center we want. We'll just say it's centered at 8. So we'll build this out with our Taylor polynomial, centered at 8. 1/12 x minus 8, and then minus 1 over 288 x minus 8 squared. And this is only to the second n. So we stop at n equals 2 over here. And we're going to try to estimate the cubic root of 11 with this particular polynomial right here that we've created. And so that's just going to be p sub 2 of 11 over here. This is the polynomial. We're plugging 11 into there. So the polynomial is p sub 2, 11. So that means plug 11 into this x right here. I know it's kind of complicated in terms of how they denotate this, but it's just plugging 11 into this x. And when you do that, you get 2.21875. That's a pretty good approximation of the square root, or the cubic root of 11. Okay, so now that we've estimated the cubic root of 11, we know that there is going to be a remainder left, right? Because it's not exactly the cubic root of 11, there's still a little bit left. So to solve for the remainder, we just say r sub 2 of 11 is going to be equal to f triple prime, because it's n plus 1 and is 2, triple prime, and then you're going to need to plug in c. We don't know what c is. We're going to have to figure that out. But it's also n plus 1 over there, so it's 3 factorial there, and then 11 minus 8 to the third power over here. This is a, and then this was the x that we plugged in there. And so the only thing we need to solve now is the f prime of c. F triple prime of c is going to be equal to, once you start doing the triple derivative of that thing, you're finding that it's going to be 10 divided by 27 x 8 to the third. Okay, this is just the triple prime of the cubic root of x. And then what we want to do, this is the magic, we're going to plug in the maximum value between a to x. So remember, we're trying to find this m, this max right here. We got to try to find what will make this equal to a maximum. How do we get this equal to a maximum? In this particular case, if we plug 8 over there, then it will be a bigger number than if we plugged in 11 over there, because the denominator is going to be smaller if it's an 8. So that's going to be a bigger number, right? So in order to get a maximum, all we've got to do is plug 8 into there instead of 11, because 8 to 11, 8 is going to be the thing that makes this a bigger number. Bam, we plug that in there, and now we can get our answer for the Rx, and once we do all that math and stuff, right? But the key here is to remember that this remainder, if we take the limit as n goes to infinity, that the remainder needs to be equal to 0 as that goes greater in order for this to converge to f of x. In order for this to be a good approximation, the remainder has to become 0 as that goes to infinity. If it's not, then that's not a good approximation. So it won't work, but if you did the math right, it should work out properly. But anyway, the idea is that, yeah, so you got to figure out whether the remainder is going to 0 as the limit of n goes to infinity, and you go into this, all these calculations. So it's a little bit more math stuff, but yeah, this is kind of the remainder business. It's kind of interesting. So a few final notes. This is going to be on binomials. We can start using Pascal's triangle. We're going to start building Pascal's triangle. And let's see if you can notice this. So we got 1 plus x to the r power is going to be equal to the sum of r. This is r over n, but without a dividing. This is rn. It's like r with the sub n here, parentheses in there. This is really, really weird stuff, man. It's totally new, but don't get too confused. If I just say r sub n like that, it just means that r factorial over the n factorial times r minus n. And let's try to build out Pascal's triangle with some examples. So we'll plug in 1 plus x to the 0 power. That's just going to be equal to 1, right? If we go 1 plus x to the 1 power, that's just equal to 1 plus x. There's the coefficients in front, which is going to be 1, and then 1, and then here's 1. Okay, and then the next one, we've got 1 plus x squared is going to be equal to 1 plus 2x plus x squared. And this is 1, 2, 1. So 1, 1, 1, 1, 2, 1. And then over here, we got 1 plus x to the third would be like 1 plus, it should be 3x plus 3x squared plus x to the third, because it would be 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. And so now we can start to build out Pascal's triangle. This will continue if you did that. These are basically the coefficients of these binomials as this increases. And this is how you would sort of represent that as it's going, because remember that r and n are going to be the same. So over here, n would be 3, r would be 3. Okay, so you start with the n equals 0, n equals 1, equals 2, equals 4, and blah, blah, blah. And so now you can build out these Pascal's triangles using the binomial theorem stuff over there. One last thing you can do with these power series is multiply them together. And that's going to be kind of a long foiling process. So we'll do that at the bottom over here. Let's say we had this thing right here, which is 1 over 1 minus x times 1 over 1 minus x squared. You can rewrite this by saying it's like 1 over x, 1 minus x on that side times 1 over 1 minus x squared on that side. And that will just equal, what's 1 minus x? It's this over here. It's 1 plus x squared. And then what is 1 minus x squared? That was this one, right? That's going to be 1 plus x squared plus x to the fourth. And now we're going to FOIL. Okay, and you have to FOIL all this stuff, and sometimes you have to FOIL even more, but this one isn't too bad. So it's just going to be 1 plus x plus 2x squared plus x to the third plus 2x to the fourth plus x to the fifth plus x to the sixth. And that is how you might want to FOIL out some of these power series if you have to do that. So hopefully you enjoyed these kinds of videos. This is basically going to be the end of the integrals, and it's going to be time for Calculus 3 pretty soon. So hopefully you enjoyed this stuff, and like and subscribe. Thanks for watching.